All right, welcome back. Now we're going to do another example. This is great. So this is fruit fly population. So fruit flies, by the way, the technical term or the scientific nomenclature for a fruit fly is the Drosophila melanogaster. I learned that many years ago in AP Bio. But anyway, so Drosophila melanogaster. That was a tongue twister. I had to practice that one. Drosophila melanogaster. Drosophila melanogaster. What was another one? Oh, aspirin. Acetylsalicylic acid. Acetylsalicylic acid. So you tongue twisters. So whenever you're taking biology, if you ever want to know what aspirin is, it's acetylsalicylic acid. So anyway. Okay, so anyway, go on. So it says, suppose a population of fruit flies, Drosophila melanogaster, increases at a rate of g of t. So here's a growth rate again. G of t equals 2 times e to the 0.02, t. All right. In flies per day. This is fruit flies per day. Okay. So it's a rate formula. Okay. If the initial population of fruit flies is 100, so initial population, and we're going to go with capital G, so G naught is equal to 100 flies. How many flies are in the population after 10 days? Okay, so we're going to let G of t equal the amount of fruit flies. Now, because this is a rate function, remember, in order to get total amount, we're going to integrate, right? Because total amount is the area under the curve. So since we're looking for the total number of fruit flies, then we're going to integrate this rate function. Okay? So remember, the integral of a rate function gives us total amount. So we're going to integrate g of t dt, which equals the integral of 2e to the to the 0.02 t dt. Now again, I can pull the constant out, so that's going to be 2 times the integral of e to the 0.02 t dt. This is where I can do my u substitution, so let u equal 0.02 t, du then becomes 0.02 dt. Again, I don't have a 0.02 there, so let's just divide everything by 0.02, and I get that. So now let's do the substitution. So I get 2 times the integral of 1 over 0.02 times e to the u du, which then becomes 2 divided by 0.02 times the integral of e to the u du, which then becomes what? Well, this is just going to be 2 divided by 0.02, which is 100. 100 times, what's the integral of e to the u? E to the u plus c, right? And again, even though I'm distributing across c, it's going to be absorbed by the c. It's just going to give another constant. So I'm just leaving it like this. And so my final answer is 100 e to the u, which what was u? 0.02 t. And notice here, and maybe you've noticed a pattern, but the 100 matches the initial population. So if you remember from algebra, remember the general population growth for any population growth that was exponential? It was always a of t equals a naught e to the kt, or p of t is equal to p naught e to the kt, right? Where a naught was the initial amount, or p naught was the initial population. They're all pretty much the same. So this kind of tells me my gut feeling that, hey, I did it right, okay? Because this is giving me my initial population. Now, in the last problem, let's see here. The last problem didn't give us natural exponential. And the problem before that really wasn't the same situation. So this is the first time where we're dealing with a growth situation. So this helps us, okay? Okay. So now what? Now we're going to use the initial information that we have 100 flies. So here's the thing. The initial population is 100. When t is 0, this is 1, so we get 100 plus c, which means c must be 0. So in this case, the constant is 0. In the other cases that we dealt with, the constant didn't turn out to be 0. All right. So now, let's plug this in. Q of 10 equals 100 e to the 0.02 t, times 10. And so that's going to be e to the 0.2 and what do we get? So let's take the calculator and let's see what we get. Okay, so we get, we're going to do, let's see, e to the 0.2, and then multiply that by 100. And we get approximately 122.1. So we're going to round that to the nearest fly. So we get 122 flies. All right. So now, there we go. So that's the population. Now, there's another way we could have done this. Okay? So let's do it the other way. Either way would have been fine. So I used total change, right? But we could have used the net change theorem. The net change theorem says, hey, if I start with the initial amount, G naught, and then add on the amount that it grew, well, what's that? That's going to be the definite integral from 0 to 10 of what? 2e to the 0.02t dt. Okay? And so this gives us the net change, remember? So this is going to give us the net change from 0 to 10. Okay? So I can start with this. So we already know what this is going to be, right? This turns out to be, what? It's going to be G naught plus 100, oops. So it's 100 e to the 0.02 t, right? Evaluated from 0 to 10. Right? And so this is going to be 100. And so what do I get? I get 100 plus what? 100 times, now it's going to be evaluated at 10, so this is going to be e to the 0.02 times 10 minus e to the 0.02 times 0, which is going to equal 100 plus 100 times what? This is going to be e to the 0.2 minus e to the 0, which is 1. So then I get 100 plus 100 e to the 0.2 minus 100. Well, look at that. The hundreds drop out. I get exactly the same thing I got before, which is again going to give me approximately 122 flies. So either way, I got the same answer. Okay? Okay. Have a great day.